后人看的，还有喜欢书包，看了再说的。
那买好书包，
这个音响买了，
我70就
不算
连税都
他给你提高，
先全是3
是不是太多了？
对呀。
那个得选。
真的吗？那真的是真的。
所以那服务员这块儿，估计都快到了。Yeah, for us, it's so 10 pages for each person. 10 pages.
1分都给不了，我1毛都给不了。他说是今儿买车那个，哎，他让自由，让我给他转买票，我觉得。
iPad 这样就可以。
我早就认清我这个事实。是白显胖，不是胖显白。我这个怎么？姜胖白胖。
要标。
All right, let's try to get started with lecture 22 and try to pick up from where we left off last time. Let's see if I can get this on one slide here. So last time we were talking about block convolution and the reason for that. And we got through one of the algorithms called overlap save. I think we're going to be done with that one. And there's an example in the presentation notes that you can look at if you want to refresh your memory. But today we're going to cover the overlap add algorithm, which is a lot easier, you'll be pleased to see. So first of all, why do we do block convolution? And as a reminder, we do it because you can't control the length of the signal. You don't want to have an indefinite length signal that you have to wait till you collect before processing. Like the example was the radio. You turn on the radio, you want music coming out. You turn on a radar receiver, you want things coming out as fast as possible. So you don't want to wait. So this is the reason for these algorithms. Let's go to the slideshow here and talk about the overlap add. So I'm going to reuse the same input signal, x of n, which has values we'll just call a, b, c, d. It doesn't matter. And the ... means it's indefinite length. It could have thousands of values. We don't know. It's a received signal perhaps, or some other signal of interest. And just so we can kind of visualize everything on one slide very easily, we're using an impulse response, h of n, which is only 3 values. It's only a length 3. 1, 1/2, and 1/4. So pretty simple impulse response. Now, what we want out, and this is a reminder of what we want out, is we want to convolve linearly these two signals, h of n and x of n. That's the output that we desire. And so y of n is h of n convolved with x of n, and I've written it down here. And because the form of h of n is so simple, it's only length 3, the terms and the output are at max only contain 3 terms or 3 values, like what, c plus a half b plus 1/4 a. And hopefully by staring at this you can see in your mind's eye h of n. If I flip it over and I move it, yes, at this value c I will have 1 times c plus a half times b plus a 1/4 times a. Ergo, I have that here. So that's what we're trying to achieve. Well, let's kind of go through this step by step with I guess some of the philosophies in mind. So this first bullet says, suppose a 6-point DFT is available. And that's really basically saying, all right, you're a design engineer, you have so many resources, you have certain things that either given to you or forced upon you. And this is one of those things that you happen to have available. It's a 6-point DFT. It could be anything, but I had to make up a value for our problem. So this is not something you necessarily chose, it's something that is available. So we're assuming that using this is a good idea and not throwing up your hands and saying, nope, can't do it. I need 8 or 1024 or whatever. So suppose we want to make it work with the 6-point DFT. So that means the length of the DFT is 6. Now the second bullet, this overlap add method is based on linear convolution. So that's the philosophy. Remember on the previous algorithm, the overlap save, that was based on circular convolution. And we were just saving portions of the circular convolution that were basically equivalent to the linear. But this is not the case here. Here we're striving to have the output of the DFT be a linear convolution. So overlap add based on linear convolution. And remember from our previous discussion, okay, if the length of h of n is p, convolving that with an L-point sequence results in an output length of L plus p minus 1 if you do a linear convolution. So with that in mind, we go to the next bullet, which is the good news. Circular convolution is equivalent to linear when you implement it with DFTs that are the appropriate length. Right, and that was the key. If you had a DFT of length L plus p minus 1 or greater, then when you use the DFT to compute the convolution, the circular convolution that the DFT does would be equivalent to the linear, which is what you want. Now, it would be very easy if the signal stopped after a certain period of time, but it doesn't. It goes on forever. So if it's going on forever, you're going to have to divide that signal into sections. And so that's this bullet here, which is you're going to divide the indefinite length sequence x of n, because it never stops, into sections of length L. And this L is what? It's DFT length minus p plus 1. And where did that formula come from? Well, we want the DFT length to equal L plus p minus 1, so solve for L. It's about that easy. So that means when you divide this thing into sections, each section is going to be L length long, so that when you take the DFT and use it to implement the linear convolution, a 6-point DFT will give you a linear convolution output. And why was that? Because in our case, L is going to be 6 is the DFT length that was given to us, minus 3, that's the P, that's that little tiny impulse response that we're playing with in our toy problem, plus 1, that's part of the L plus P minus 1 formula, so we end up with 4. So let's think, what does that look like? We've got our indefinite length sequence x of n, and we are simply just going to slice it up into sections of length 4 for processing purposes. So A, B, C, D, E, F, G, H, I, J, K, L, and so on. So we're just going to slice it up. So if we remember, how does this work? Well, let's take it one step at a time. Our first section is our first group of signals, or I guess our first little group of A, B, C, and D. The D somehow disappeared on us, but it's there. And we're going to convolve that with H of n, and we want a linear convolution. Well, we know from all our DFT work that if y1 of k is x1 of k times h of k, that's multiplying the DFTs of those, then the y1 of n is equal to the circular convolution of x1 of n and h of n. So if this is the case, then this is the case. So that's why we can take the DFTs, multiply and do an inverse DFT and get back to y1, because that's what we really want. Now, why didn't we get any aliasing or get in trouble here is because we purposely made sure that did not happen. We selected L. L was 4. Why did we choose that? Because 4 plus 3, the length of the impulse response, minus 1 is 6, right? And that was the length of the DFT, so there's no aliasing, and the output of this process is going to be a linear convolution. So let's suppose we do the circular convolution with a, I guess, size 6, but that's the same thing as basically taking a 6-point DFT of x of 1, take a 6-point DFT of h of n, so what is it? That's 3 little zeros here before you put it into the DFT. Multiply those and do an inverse DFT. What do you get back? You get back this sequence here written below. And notice here we have 1, 2, 3, 4, 5, 6 outputs, just like we thought. So we put in 4, we got out 6. So keep that in mind as we move along. Our second section, kind of second verse, same as the first here to some extent. We have E, F, G, H, and our same impulse response. So we do the same thing. We convolve these guys using the DFT, and there's no aliasing. And if we spit those out, what do we get? We still get 6 outputs. 1, 2, 3, 4, 5, 6. Now, the key part of all this, the only bookkeeping part, is where are the indices and where are the outputs related to each other. So notice we kind of started at index 4, 5, 6, 7. So if we got an output, what do we expect? We expect the first output at 4, then 5, 6, 7, 8, 9, and it keeps going on and on, because there really is nothing before this section. We're kind of processing them independently. If we take our final section, it's basically the same thing. 8, 9, 10 is where it starts, or 8 is where it starts. We do the convolution just like we did before. We end up with this output, which is a linear convolution, no aliasing. Everything seems fine. Now the trick is stitching these all back together. That's where the overlap add, the add part of the name, comes in.
Wasn't there a fourth section?
There might have been. Let's see. Yeah, I guess I kind of I got bored of showing that at that point. But because they're all kind of the same, the only thing that's really changing here is these A, B, C, D, E, F, G values and where it starts. And that's kind of where we're headed, because we're saying, note that the indices for the output of these convolutions overlap. And that's the overlap in the name, and we have to add them together. If we go back, because you might have missed it, we start at 0, we input 4 here. We get out, starting at 0, we go to what? 5. But then we selected things here at 4, and we go to 9, right? That's the output. So you can kind of see, wait, that means these outputs here, like at 5, are going to overlap with these outputs here at 5 as well. So if we scroll down to the end, I tried to show that by saying, okay, let's process each one of these sections at a time, 1, 2, 3, kind of lay out their outputs and see where they line up from an index standpoint. And that's what these are for. So Y1 is this first series here. You can say, okay, great, we've got our outputs, and there's no aliasing because of how we formulated the problem, or how we accepted, I guess, L number of inputs at a time, which turned out to be 4. So we chose that to prevent aliasing. But notice as we sectioned it out, Y2 has outputs at 4 and 5, which overlap with Y1. Y2 also has outputs at 8 and 9 index, which overlap with Y3. So if we just add these up, so you keep track of this bookkeeping, you end up with Y of n, which is just a linear convolution. So you can kind of see it works out, and I think it's it's fairly straightforward to understand.
Was there
Question?
no, overlap in G, F, for 6 and 7?
Let's see.
Is that because it's just like in Y1 and Y3, there's no 6, like it doesn't start at 6 or something. It just starts at 8.
Right. It just turned out it was just that way, just because of the way the lengths of the sequences were. I mean, if we changed the problem so that the length of the impulse response was longer,
Yeah.
then you'd have, you think you'd have more overlap? Maybe. Let's see, because you'd have to reduce the size.
Because you do like a convolution with 6 points, but then doesn't. So the 6 and 7 would be like the 2 extra points in the link, the DFT link, or in this case.
In this case, all the data in that section that you needed to process it was there. That's kind of what it comes down to. I mean, if you go back to 6 and 7, is that here? If you think about trying to convolve h of n with just this sequence, you flip h of n over and you're moving it across. Everything you need to get output 6 and 7 is in that sequence there, right? Because the output of 7 right here is going to be what? 1 times h plus a half times g plus a fourth times f.
Okay.
So there's nothing else that you need to produce that
That's the nature
output.
of the-
Yeah. It's just the nature of the lengths of these sequences that turned out to be the output. Now I think, let's see, save. All right, what happened here? Overlap add. I thought I had a sort of a summary here. Overlap save. Okay, so I guess that's kind of the final piece of the puzzle here. Now, overlap save, I think we already summarized this one. That's a different algorithm. Overlap add. Yeah, so I just did 2 extra examples in here that you can look at kind of offline here to get another example. And I think what we'll do is we'll stop here with these and get on with today's thrust, which is basically computation of the DFT. So computation. And the reason this is important is because everything else that we've talked about using the DFT to do linear convolution is kind of just academic exercise unless you can efficiently implement it in processors. So let's look at sort of the structure of this equation, and that sort of brings out the efficiencies that we're going to exploit and learn about today. That's 2 pi nk over cap n minus 1. And the inverse DFT. I think what I'll do is now when we look at these equations, they look pretty similar for the most part. Just a few things different. Just the sign of the exponential. So not going to affect anything really from a computational standpoint. That doesn't matter. It's still going to be complex multiplies. So anything that we discover or use for the DFT will equally apply to the IDFT, the inverse DFT. Now, to make things a little bit easier to write down, and also when we're documenting our like flow diagrams, we're going to use this nomenclature, which the book also uses, which is instead of writing e to the minus j2 pi over cap n, I'm just going to write capital W subscript n to represent that. And that's a little bit of a convenience for some of the things that we'll be annotating. Now, as it turns out, you can kind of see this factor here is a big part of the factors here and here. Right? It's just going to be capital omega sub n with a small n raised to the small n and k power. So, as it turns out, where are all these efficiencies going to be found? And it turns out to make this an efficient procedure, we're going to exploit the periodicity. Basically periodicity and symmetry. Raised to the nk. That's really what it comes down to. So let's just take a look at a few of them just to kind of get you thinking about how this works. So that's 2 pi nk over cap n. And what, n comma k, either of these indices can be 0, 1, dot, 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 n minus 1. Right? Well, right off the bat, you can tell that if either n or k is equal to cap n, you end up with what? E to the minus j2 pi, and the n's cancel, or the capital N's cancel, and you're left with just some index times e to the minus j2 pi, which is always going to be what? Some integer number of 2 pi, right? So it's always going to be 1. So there's not much to see there, right? So Wn k, and I'll make this a capital N, is the same as n capital N, which is the same as 1. So as we move through some of these, you can kind of see it's going to clean it up. Also, if we go ahead and exploit the periodicity, let's say we have k plus capital N, that's going to be the same as Wn, and let's go to let's make it the same as this. So it doesn't matter whether k is plus capital N or n is plus capital N. And why is that? Because we're exploiting the periodicity in n. So it's periodic in capital N. That also means that we can subtract n as well as add n and not make much changes to it. So if we were to do that, let's take k to the capital N minus n. Then factor this out, so we'll get what? Capital N, kn, which we already know what that is. K times minus n is minus nk. We already know this is just a complicated way to write 1, right? So we end up with minus nk, which we can write also as a nk entire thing conjugate.
Why
Which
is
is
it equal to 1?
e to the minus j2 pi k capital N over n. So that should be e to the minus j2 pi k. And k is an integer n minus 1. So I guess I'm asserting that whatever you take k to, this is just an integer multiple of e to the minus j2 pi. So it's just flipping around the unit circle over and over again, k times. So that's why that It's just a fancy way to write 1. Now the next step is we're going to try to count the number of complex operations, because that's usually what you have to worry about, or at least what we're going to use as a meter. And of course, if you're familiar with hardware and everyone benchmarks, and oh, I'm a faster processor, no, that processor's faster, they have what they call like benchmarks or things that they try to do. And so you can measure that with, I don't know, number of FFTs, or you could do some kind of graphical processing. Well, for today's lecture, we're just going to try to look at algorithms and the number of complex multiplies. That's our metric. So complex multiplies is the metric. And that's usually a reasonably good metric because a lot of these applications, we're going to be using complex sequences. So let's look just right off the bat, just so you can kind of, I guess, get warmed up. Let's look at the cost of the complex operations. Because at the end of the day, hardware doesn't know if it's a complex operation, right? Hardware just knows there's a number in a register and it does something to it. And whether that's real or imaginary or something else is our interpretation. So if we just had 2 complex numbers in general and we wanted to multiply them, what, AC plus JBC plus what, JAD minus BD. So that's going to be 4 real multiplies, or mults, so I'll abbreviate. And then if we add this up, plus J, what, BC plus AD, we've got 2 real adds. So every time you actually do a complex multiply, you've got to cash it out in terms of 4 real multiplies and 2 real adds. And you can do that, but we're not going to do that for today. That's one extra step.
The J is also real? Like, that's considered real?
No, a J is just, you just put like this one in one register and this one in another, and you treat them as however you want to treat them. Like if we had to, if we were doing some multiply operation, each of these numbers would be in different memory locations, and it's your interpretation of what they are. In fact, one of the homework problems is to look at a DFT algorithm and say if you swap real and imaginary, do a forward FFT, or forward DFT, then swap real and imaginary, is that the same as doing an inverse FFT? And so,
Is that
yeah, I know the answer.
no, is that no, like, is that okay?
That's right. Hopefully you go through and see it, and then we'll, I guess the homework's due on Friday, so we can, we'll talk about it at some point. Yeah, you could probably Wikipedia that one. So let's see. And for, I guess, complex addition, you've got the same situation, right? So if you have A plus JB, C plus JD, and you want to cash this out, it's A plus C, B plus D, so it's going to be 2 real adds. Because firmware and hardware, they don't know that it's complex, they just know there's a number in a register. So this is the kind of stuff you do when you really want to get down to the very bottom of what's happening. How many floating point operations or operations per second are you going to actually have to stomach to get it done? So to start off with our accounting, kind of digital signal processing accounting class, we're going to start with calculating one DFT value. Just look at one, and then we'll move on from there. So we go back to our handy formula. What, n equals 0 to n minus 1 x of n. This time we'll just use our notation. Make things a little quicker to write down. So we've got our expression. Well, let's expand it and just look at the terms, right? So x0, the very first one, well, n is 0. K could be anything. Not that it matters for that term. x1. Now n is 1 times k. Now we've got x2, and you see the pattern until we get to the end. And that's what? N minus 1 times k. So we've got our entire thing written out. But what's going on here? Except for the first one, which is not really a complex multiply, right? Because anything to the 0 power is 1. So any smart hardware really wouldn't count that one. But all the rest of these are just going to be one complex multiply in general. So to get out one value of k, it's going to take, if we count them up, 1, 2, 3, dot, dot, all the way up to n minus 1. So we started with 0, n minus 1. It's n values. So it's n complex multiplies. And if we don't search too hard for too many symmetries, we can say, well, if I change k, so I'm going to a different one, each one of these omega capital W values change, so then it's a different number, so it's a different multiplication, right? And so this is just good for 1, and also what we've got n terms, so we've got n minus 1 complex adds that we have to get done. So suppose you don't want 1, but to compute all n values, right? Because what? K was 0, 1, dot, 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 n minus 1. Right? So we've got n different values to compute. So that's pretty straightforward. N times n squared complex multiplies. Which I'll abbreviate complex mults. And n times n here is n squared, n times minus 1 minus n. So that makes me at complex adds. So when we look at that, we can say, well, sometimes we don't really need to get into the distribution of all these things, and we just want to talk about operations, or complex operations. So a DFT operation in general is proportional to n squared, because you have n squared complex multiplies and n squared complex adds. And so that's why you might hear phrases like an order n squared operation. So I'll put that in scare quotes, an order n squared operation to do a DFT. So all that turned out to be too inefficient for most applications a long time ago in the early days of computing. So what did people do? Rolled up their sleeves and spent a lot of time on research and development and mathematics. And so a lot of people spend a lot of time trying to make this a lot more efficient. And so kind of the output of all that industry into making it efficient is kind of known as the FFT. Or fast Fourier transform. And really that's not just one algorithm. I think when I first learned this stuff I thought, oh, a fast Fourier transform is a radix 2 algorithm. Well, that was sweet and naive, but that is nothing could be farther from the truth, right? It's really a family of algorithms. So it's not one algorithm, it's a family of algorithms. I should say family of algorithms for efficient DFT. I'm going to use the word implementations which is a little bit long, but because it goes even beyond nowadays, it even goes beyond just the slick mathematics and clever tricks to reduce the number of computations. And traditionally, they exploit the periodicity and symmetry of the DFT and that complex kernel. And I think one of the keys, one of the more modern keys, is that the modern versions pretty much exploit the hardware that you're using. So the hardware architecture and resources. So I'll just put hardware resources. And that's kind of the FTW, fastest Fourier transform in the West. You can look that up. And that's very sophisticated, where it goes out and you install it. It creates what's called like an FFT plan. So it looks at the resources that are available at that time that the FFT is going to be implemented. And then it creates an algorithm based on the hardware that's going to be available, the memory and everything, and then uses that. Because a lot of times the slickest algorithm may not be the fastest, depending on how the hardware is. And if you're experienced using GPUs, you know a lot of bets can be off. So what we're going to do is kind of skip this part here, because that's very application dependent. What hardware resources do you have? And just look at kind of the beginnings of how all this started and the things that I think are the big takeaways. So we're going to look at two algorithms in detail: decimation in time and decimation in frequency. Because if you kind of understand the big picture of those algorithms, then you'll get the idea of how to implement things efficiently, or at least the major concepts. And we can kind of demo this in MATLAB and go through the math, and I think you'll understand the utility of it. So decimation in time. And so the major idea of this is to take your input sequence and divide it into successively smaller subsequences over and over and over again in a divide and conquer type of approach, hence the word decimation. So that's sort of like downsampling decimation. So it's going to split it into two smaller DFTs, or 4 or 6, 8, etc. So we're going to go through a simple one where we'll start off and say, well, let's let x of n be length n, and let n be divisible by 2. So right now it can be divided by 2. And so as we start off, and the only thing we know right now is n is divisible by 2. We start from here and say, okay, if it's divisible by 2, let me break it into two sequences: an even sequence and an odd sequence. And you've seen this before, but that's how we started off with the polyphase derivation, right? So we can take a sequence and break it into two pieces. So I'm going to do 2n, and n is going to go from 0 to n over 2 minus 1, which is valid because I know n over 2 is an integer, n is divisible by 2. So that's so far so good. So for every single one of these values, x of 2 of n, this is going to give me the even values, right? But I need this n to agree with that n. Because if they don't, you can imagine that different values here would go with different complex kernels if I didn't. So we can put that in play. But what about the odd? So let's do the odd. It will also look the same. But now we've got x of 2n plus 1. And our kernel is going to be a little more complicated because it's 2 pi times 2n plus 1 times k divided by n. Now, before we start messing with this any further, let's just remind ourselves what the goal is. Goal. Make this look like 2 n over 2 point DFTs. That's the nature of the approach. We keep trying to break it down. And why does that work? Because it's proportional to n squared. So now if we keep breaking it down, it's going to be proportional to n over 2 raised to these powers squared. So the key is, how can we manipulate these expressions to make them look like n over 2 point DFTs? That's where we're headed. So the first part is fairly straightforward. Let's look at the even sequence first. What do we have to do to make this look like an n over 2 point DFT? Well, wouldn't it be nice if n over 2 was in the denominator here? And I happen to have a 2 here that I can just stash down there. And then this goes from 0 to n over 2 minus 1. And so we're well on our way with the even sequence part. So let's make that adjustment. 2n e to the minus j 2 pi n k divided by n over 2. So divided by n over 2, that 2 comes up and it's the same as what we had here. So far so good. Nothing has changed much. Now what about this one? So if we multiply this e to the minus j 2 pi through, what do we end up with? Well, e to the minus j 2 pi times 2n times k divided by n. But that's the same thing we had up here, so we can do that trick again. That's not really a problem. But we've got something else left over hanging around. We've got the e to the minus j 2 pi times 1 plus k, or I guess that's e to the minus j 2 pi times k divided by n. And the trick to using that, or the key to using that, is to realize that that whole factor doesn't depend on n. So we can pull that factor out, which we will. So that's going to be 2 pi k over n. And now I think we can bring this on up. Say, now we've got 2n plus 1, and everything looks like what we want it to look like. 2 pi n k divided by n over 2. So now what we have, if I can get it centered on screen, is an n over 2 point DFT plus some sort of kind of glue factor. Kind of call it the, I might call it that throughout the lecture. Sort of this glue factor here times another n over 2 point DFT. So what we want to do is we're going to give these kind of names. The even part is what we'll call g of k. And it's the DFT of the even samples. And so that's n over 2 minus 1, x of 2n, 2 pi nk, all over n over 2. And that's the DFT of the even samples. And of course we'll have another name for the odd samples, which is h of k. And it's very similar, except the inputs are the odd samples. 2 pi nk n over 2. And for both of these expressions, what's k? K goes from 0 to n over 2 minus 1. Why? Because these are both n over 2 point DFTs. And of course, hopefully you're starting to smell something fishy, because if k goes from 0 to n over 2 minus 1, I thought I started with an endpoint DFT. Well, we're going to explain that, but all in good time. First thing we'll do is take a look and say, well, is this whole concept hold water? What happened to the number of operations? Did it go down? So let's do kind of a quick accounting. And we're going to write down x of k in this more compact fashion so we can kind of point at things and count up ops. And this is our little glue phase here, which, yeah, I'll write it that way. Over n h of k, where k goes up to 0 to n minus 1 because this is an endpoint DFT. So that's an endpoint DFT. And as I said before, g of k and h of k are n over 2 point DFTs. So what's going on here? What happened to half the data? Well, as it turns out, g of k and h of k are evaluated modulo n over 2. So let's rewrite this so it's a little less or a little more understandable. Now we have x of k is equal to g of k, but now it's time for our fun modulo arithmetic. So now we have something that makes a little more sense. We've got k equal to 0, 1, dot, 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 n minus 1. So we've got an endpoint DFT, which is good because that's what we want to do. And we've got g of k and h of k, which we've computed by n over 2 point DFTs. So now let's do a quick accounting of how much does it really take to do this, right? So we know that since this is an n over 2 point DFT, I'm just going to draw an arrow and say, well, we already calculated this before. It's going to be n over 2 squared complex multiplies, right? And we said, since this is n over 2, it's going to be n over 2 squared minus, I think, n over 2 complex adds. And that was, basically we got this because the endpoint ones was n squared multiplies and n squared minus n. So if we divide n by 2, well, it's the same thing, just n over 2. Well, h of k is clearly the same as g of k, so that's n over 2 squared complex mults. Nothing new there. And n over 2 squared minus n over 2 complex adds. So far so good, but there's one thing left out, right? What about this factor? How does that change everything? Well, as I said, k goes from 0 to n minus 1, so we're going to have to make basically n of these factors, and it's going to have to be multiplied times h each time, right? So if we just wanted to compute the complex multiplies, we're going to have an n complex multiplies. And of course, if they add these two together, it's going to be n more complex adds. Well, I think I'm not going to include that one just yet, because mostly we're going to focus on the complex multiplies because they're just so costly. So I won't write it on this page. Maybe I'll write it on the other page. So let's add up the bill for all this. So the total complex multiplies. So for g of k, we've got n over 2 squared, but then we've got h of k, which is the same. So we've got to add that on. Another n over 2 squared. Then I've got my n complex mults for this kind of glue factor here that glues these two DFTs back together. So we have to add that on. And so what is that going to leave us with? N squared over 4 plus n squared over 4 is n squared over 2 plus n. Now let's look at the total complex adds. And if we do that, we've got n over 2 squared minus n over 2. And that was just the cost for g of k. But I've got the same cost for h of k. So we've got to tack that on. And then we've got what left? We've got, then we have to add these two sequences back together. H of k times this, that's one factor, plus that. And that's going to be another factor of n. So this is easy, right? N, that's minus n over 2, minus n over 2, so those two cancel. And so we're left with n squared over 4 plus n squared over 4. So I think that's just n squared over 2. All right, so we calculated it all up, and we've seen that it's, hopefully we can see that, okay, this is okay because we're getting a reduction. We went from n squared to n squared over 2 with an tack on of n. So let's think, what could we do next? And what we could do is keep going, right? We could take it further and say, if we did it once and it was good, why not twice? So let's start off with our two sequences, and let's try to make things compact here. This is going to be what? N, K, and we end up with K, and this is n over 2. So we broke that up, and now we're going to say, well, let's break up G into a sequence P plus, and we'll make this a I'll try to make it fit on my slide by compacting it down. And that's going to be K, but it's n over 4. So G now is this stuff. We basically just took our same expression and iterated it. Said, well, if X could be divided into two n over 2 point sequences, then this n over 2 point sequence could be divided into two n over 4 point sequences. Right? We just have to keep track of what's going on. And so why not do the same with H? And so we'll just keep it up. And that's K. And we'll make this S. So we're just breaking it up further and further and taking a look at what happens.
What's the point to break them up?
We're reducing the number of complex multiplications to compute the final DFT. And so when we do a DFT doing the brute force method with none of this breaking up business, it's just n squared. What we found out was when we broke it up once, we got n squared over 2 plus this almost nuisance factor, because what's really driving you and killing you is the n squared. So as we keep going down, we're just going to go This is probably our last move down here. But since we know the complex mults for those two n over 2 sequences is n squared over 2 plus n, we can just replace n with n over 2 again, right? And so we'll end up with, this guy's going to be, what? N over 2 squared over 2 again, which is a half, and then that whole thing is plus n over 2. And we strike again with the same thing here. This is just the complex mults needed. And I'm using that as sort of a proxy for complexity. We know they're expensive, right? They're like 4 real multiplications and then 2 adds. So let's add up this one and kind of see where we stand. So the total complex mults for this last breakup was 1/2 n over 2 squared plus n over 2, and that's just for the breaking up of G into P and Q. But then we've got to also pay for the breakup of H into R and S, which is n over 2 squared plus n over 2. But then we've got to add them both back together again, right? So once we've done all of that, that's going to be another, I think, plus n, and that's to add G and H. Because remember, this is just for getting G and H, but we've got to add them back together. Or wait, this is complex multi, so this is not adding, but it's multiplying that final factor. Sorry. Multiply by W and K. That's at the end. So after we multiply H times this, then we can add it back together. So let's add that up. We get n squared over 4 plus 2n. N over 2, n over 2, and n is n. Half plus a half. Leave n squared over 4. So I think that one's pretty straightforward. Now let's try to summarize what we're seeing here. Because where we're going is we're trying to get you insight into what's the limiting factor in all this. Where are we going to end up eventually if we had the most efficient algorithm that we could for breaking this down? So we have a DFT and the complex mults. And we saw right off the bat that if you did an endpoint DFT, it was n squared if you didn't do any decimation in time. If we did the decimation in time once, or we'll just, maybe we'll call it decimation in time 2, it was what, 1/2 n squared plus n. And we did decimation in time twice. Maybe this is once, twice, and that was 1/4 n squared plus 2n. So where is this going? Well, first of all, you could say, well, how many times can we divide n by 2, right? Eventually, it won't go anymore, and we're done, right? So how many times? Will 2 divide n? Well, the easy answer is log 2 of n, right? 2 times 2 times 2, so many times. So we know we can go that many times, but what is the cost to reconstruct at each stage? So what is the cost to reconstruct at each stage? Because that cost is what you're going to have to pay log 2n times. Right. And so what we're going to try to do is show you, not rigorously, but somewhat heuristically, I think, how this works. And we're going to just go through and see the cost of doing each reconstruction. And so we'll make a little table with the method on one side and the cost on the other. And the cost is, of course, in the units of complex multiples. And we know right off the bat that if we just use the brute force DFT, and I guess we'll say x of k sum x of n, just sort of write it shorthand like that, we knew the cost was n squared. We went through that in detail. Our next step was to say, well, we could break x of k into g of k plus nk of h times h of k. And we went through that, and the key part of our analysis now, instead of writing down that complicated expression or trying to add up all the terms, we're just going to look at the cost of reconstruction at each stage. And what is the cost? Well, this is an endpoint sequence, right? And we have this multiplication factor here, and it changes with each k. And k goes from 0 to n minus 1. There are n of them. So the cost is going to be n complex multiplications plus the cost of g and h. So I'm just sort of writing things down a little differently to see if you can see the pattern. I'm going to say, okay, g and h we got to pay for, but we also got to pay for this reconstruction. Now let's go one step further and say, well, now I'm going to do it by the method of g is equal to p of k plus, what's this one, n over 2 k, and that's q of k. And then we're going to break h into what we're using, r, and this was s. And then we have to put it all back together. You can never get away from the g of k plus h of k. At the end of the day, we got to put it all back together. So what's the cost of this? Well, if we go back up to this g of k, these two sequences are what? They're n over 4, but this one's n over 2 because g of k is n over 2. So this factor here, this kind of glue factor, is what's driving us. So that's going to be, since g of k is an n over 2 point DFT, it's going to be n over 2, but plus the cost of what? P and Q. Right? P and Q. H is the same. It's n over 2 plus cost of, now we've got what? R and S. And of course our old favorite here, X, it's going to be n plus the cost of G and H. Well, if we add these up, we've got n over 2 plus n over 2 is n, plus another n is 2n. So it's 2n plus the cost of this other stuff. So n, 2n plus the cost of everything else. And our final example is, suppose we took it one more step and said, you know, let's let P equal AK plus W. This is n over 4 to the k, and we'll call that B of k. So this is going to be what? How many? If we took P and break it into these two sequences, P is an n over 4 point sequence. these guys are n over 8. So to glue it back together is n over 4, plus the cost of this other stuff. And the point of it is, if we break up Q into something, R, S, this is starting to get a very long list, but you have Q, R, S, and G, and H, and finally X. What do we have? Each one of these is an n over 4 point sequence. Why? Because each of them requires this. G we already know because G is an n over 2 point sequence. So is H. And X is an, let's see, S is n over 4, off by 1. And what was X? It was an n point sequence. So if we add all those up, n over 4 plus n over 4 plus n over 4 plus n over 4 is just n, plus n over 2 plus n over 2 is 2n plus 3n. So you get 3n plus the cost of these other factors. Now, what turns out is that if you have this process going all the way down to a 2-point DFT, what are we seeing? Each stage, just to reconstruct that DFT for the next level, costs n complex multiplies. So if there are log 2 n stages, then what we end up with is the decimation in time DFT is going to cost you a lot less. The decimation in time DFT complex mults are on the order of n log 2 n. And that's where the enormous amount of efficiencies are gained, so you can actually do a lot of this quickly. Now I think what we have with the time remaining, I wanted to do one example where n is 4, and then as we go through it, we'll do kind of an example in MATLAB so you can kind of see just sort of in real time and implementation-wise how this works. So let's do an example, and we'll have n equal 4. So if we've got x of k, and we'll have n equal to 4 so we can kind of see how it all plays out. We got 2 pi nk over 4, right? And k is 0, 1, 2, and 3. So if we break it into our even and odd samples, straight away 0 to 1, which is our n over 2 minus 1, 2n, 2 pi, and this is what? We had 2n k over 4, plus our odd samples, right? And this was x of 2n plus 1. 2 pi 2n plus 1 times k over 4. So we'll do the same trick that we did last time. Move the 2 into the denominator to make it look like an n over 2 point DFT. Factor out everything and then rewrite it. So we end up with kind of a simplified version. N equals 0 to 1, x 2n, and we'll switch to our more compact notation here. So we've got 2n plus 1 and 2 to the nk. So we've got our two 2-point DFTs with our little glue kernel there. Now, suppose we use the names G and K again, for this. And actually, shouldn't have done that. It's much more compact to write that like this. So we've got our two sequences. And now we're going to kind of look at how would you implement this in MATLAB if you were trying to sort of experiment with it or to understand it in a more maybe visceral implementation way. So let's sort of go into what this really means. I think we know mathematically and arithmetically what it means. But just think about how would we do this in MATLAB.
Where'd the n go in this x expression?
The n. I don't think there is an n here. N. There should be n's here. You think there should be an n here? I think the n. Remember, there's no n in this one because of our trick of saying either minus j2 pi n. Yeah, and so this either minus j2 pi times k over 4. You can pull that out because it doesn't depend on n. So there can't be an n there if that's what you're working to. So let's take a look, and since we know g of k and h of k, well, those are 2-point DFT sequences. So, but we know k goes from 0 to 3. So let's pull out our handy table and remind ourselves of what's going on. So if we want to look at it modulo 2, which is what this means, 0 modulo 2 is 0, 1 modulo 2 is 1. What's 2 modulo 2? Well, it's not 0 or 1, so you have to subtract or add 2 until it is. Subtracting 2 makes it 0. Subtracting 2 from 3 gives you 1. So what is this really doing to g of k? In some sense, it just has the effect of just repeating g over and over again, right? So let's just write this out like it's a either a command in MATLAB or maybe a matrix operation. So instead of writing down the g modulo 2k index, let's just say g of k. Each one of these guys is a 1 by 2. So this whole thing is 1 by 4. Plus, we've got our little kernel of stuff here, but that's also 1 by 4. Why? Because k goes from 0 to 3, so that's 4 elements. And that's also times, each one of these is a 1 by 2. So this whole thing could be kind of 1 by 4. Now I guess the this is kind of element by element multiplication, not matrix math, because obviously this needs to be transposed so it would work. But you kind of see that what we've done is we've taken a 4-point DFT and sort of said, you know what, I'll make a 2-point DFT, sort of periodically replace it, do it twice, glue it back together, and we end up with our 4-point DFT. So just to kind of show you how that's done, let's go back to the PC, and you can kind of see how easy it is to experiment with it, or at least see how it goes. So let's see if we just do an experiment where let's just generate some random sequence, and let's make n equal 4, right, so we can see everything. No funny business here. And DFT of x, truth, that's FFT of x. Now we're going to start doing our decimation and time stuff, right? So we're going to say, well, I'll just call it G1 is the FFT of x, but I'm only going to take the even samples. Right? That's the only ones I want. So starting at 1, index in MATLAB, which is 0 in DSP land, H1. Now we're doing the odd, right? So we get those. But now we have to glue those things back together using that glue phase, right? Well, what is the glue phase? 0, 1, 2, 3. Those are the index. And that W is what? Minus 1 I times 2 times pi times k divided by n. N is 4, right? So now we've got it all together. And let's look at our x, k, let's call it our decimation in time, right? So we're just going to add it together. G1, G1, that has the effect of doing that modulo 2. So each one of those, right, G1 had better be a two-point DFT, right, has 2 elements. So let's put it all together, G1, G1, plus we've got omega. And I don't think it liked that because I forgot to close off this. And then we have what? DFT x truth. Look pretty similar. And if we subtract off xk dit, get almost 0. Now, the reason I like going through this is because you can literally see right there. I took a big FFT, 4, really big and scary, turned it into 2 smaller FFTs, right? And then just reused them. And I think this is one way to look at it. I like to look at it this way because it makes it really clear. You can break down them into smaller FFTs over and over again and just glue them back together. We're going to see there's ways for thinking about this, for implementing it, that you can start to see those DFT butterflies or FFT butterflies, which are an implementation thing we're going to talk about next time. So let's stop here and next time finish the decimation in time DFT. Yeah, talk about that a little bit on Monday. Or a little bit on Wednesday. Yeah, we'll talk about it 2 Fridays from now, right?
Next Monday? Friday.
Yeah, Friday. I think. I don't know. Friday evening, Friday at 5 or 8, because I want to post the answers because people want to see the answers before the exam.
I see.